Our first speaker is Pollock. He's going to speak about exact Bayesian inference for big data.
Is this on? On?
Yeah.
On now?
Yeah.
Okay. Is it on now? I think so.
Okay, great. Okay, so before I start, I've put a long list of people I'm working with. Actually, I'm not working with all of them, but the first part of my talk, which I'm going to talk about single core methods, it's work I've been doing with Paul Fearnhead, Adam Johansen, and Gareth. And latterly, we've been trying to extend it to different methodological approaches. And Divakar Kumar, who's one of my PhD students, is working on it. And Andy Wang, who I'm not working with, has been doing lots of really good stuff on the theory behind all of the first part of the talk, and he's got a good poster outside. Hongsheng Dai is somebody I'm working with for the second part of the talk, which we're calling multi-core approaches. And I've put in Marcin as well, because a lot of this work is underpinned by theory on simulating diffusions, and Marcin's also got a really good poster you should go and have a look at. So I would like to thank the organisers for inviting me to SIN. The reality is I've been SINing for 4 years as part of the ILIKE grant, and I think on behalf of all of the postdocs, I'm sure this is the case for everybody, I'd like to thank Gareth, Paul, Chris, Christoph, and I'm missing somebody actually. Chris and Christoph, that's what I'm missing. So thanks very much for 4 years. So, to start off, I listened to Steve Scott's talk yesterday, and he was talking about big data just being a fad, and I'm inclined to believe him. And I found this last night when I was trying to find cartoons for my talk, and I would agree that it is a bit of a fad, and it becomes a statement when you apply for grants or you're wanting to make your work look appealing, that you make it look even bigger or humongous. Right beside this cartoon on Google Images, I also found this cartoon, which I thought was quite appropriate for some of what I'm going to discuss. The idea that you've got lots and lots of data, but they're in lots of different places and you want to condense it down. Okay. So, when I say big data, what do I actually mean? What I mean is really the topic of this workshop, which is scalable inference. So the big problem for computational statistics is in the light of particular types of problems, such as you've got a lot of data, then typically your algorithms might suffer from all sorts of issues that you wouldn't experience otherwise. So you might be interested about robustness, or how slow your algorithm gets as you get more and more data, what it actually even means to be using particular types of models for particular types of data when you've got lots and lots of data. So, what's the problem I'm going to be talking about today? So, in a very general form, and actually this is a bit more specific than it really has to be, suppose we're interested in sampling from a target pi and it has this particular form. So C here could be the number of data points you've got, and in that case F would be the individual datum likelihoods. Or perhaps F is a sub-posterior and C is the number of cores you've got to work with. And I want to use brackets MCMC. I want to use some method for exploring pi, which has all of the nice properties of MCMC, in that you can use it for lots of different approaches. I don't necessarily want to do MCMC, but I want the same sort of class of things that I can explore. And in the context of big data, which I'm going to talk about a little bit, there are lots of different approaches for doing this. One I'm going to describe as being single core approaches. Another I'm going to describe as being multi-core approaches. Okay, so single core. What's the problem with single core and big data? Well, really the problem for MCMC at least comes down to the fact that as you're moving around your state space in MCMC, you make a move from one point to another and you have to accept or reject. And it's the acceptance rejection which is the big problem, because each time you accept or reject, every time you move to a different part of your state space, you're going to have to evaluate pi, and pi is going to be an order n calculation. So that's the issue. And the goal here, and I'm being very precise how I say this, is we want the iterative cost of some algorithm that we want to design to be scalable in the sense that it doesn't grow in this linear way as you have n, or super linearly. And there's lots of people who've been working on this and related problems. So there was a whole bunch of really nice work on pseudo-marginal type methods where they used subsampling. There's things like Firefly where they use particular characteristics of your model and they can do good stuff, and there's stochastic gradient schemes. But this problem is by no means solved, and I'm not necessarily saying what I'm doing today is going to entirely solve it either. There's lots of other approaches that people have started to work on, and a few of the talks in this conference have been really good and can be applicable here, where you look in different directions. So you don't necessarily start from the foundation of MCMC, you look at perhaps continuous time approaches. What about multicore? What is this multicore method? Well, Steve gave a talk yesterday where he described it. I'm going to add some addendums to it actually. So multicore approach would be one way of solving the single core problem. So what you would do is you would artificially break your data into S shards using the terminology, perhaps of the same size. You would, on separate computers, do manageable separate inferences. And then what you try and do is you recombine them in some way. So that's certainly one approach. This type of approach is not necessarily just for big data, but certainly something which fits into the big data paradigm. So the big problem with this is recombining. How do you do it? How do you do it in a principled way for target distributions that are not necessarily Gaussian or close to Gaussian? And there's lots of work happened in this area, consensus Monte Carlo, all sorts of averaging approaches, kernel type methods. But essentially, they add additional constraints and assumptions into this paradigm. So the constraints are perhaps you're only going to allow your computers to communicate once, or you're only going to allow communication in one direction. So there's all sorts of computer science constraints, and I'm no computer scientist, that you also want to put in here and try and work with as well. There's some terminology which I find quite confusing in the literature. The term divide and conquer is used a lot to describe this type of paradigm, but this is closer to what you might call a fork join network, in the sense that you've broken your data set into pieces and you've got one recombination step. You could also think about other approaches to multicore that are slightly outside this paradigm, where it's genuinely divide and conquer. You've got this recursive algorithm that calls itself, where perhaps you've got a binomial tree and you combine two things and then another two things and so on and so forth. So there's not necessarily just one paradigm to doing multicore, and it's an interesting thing to explore. I'm going to call it rather facetiously talking multicore and quiet multicore. So as I said, big data is not just the problem that we've got here. There's lots of scenarios where you've got this type of model structure, and perhaps you can relax it slightly and say, will I allow communication between the cores and this, what I'm calling mother core, the one that's combining all the inferences, or am I going to only let it in one direction, or not at all? This idea of what I'm going to call quiet multicore. Does that make sense? I made this up last night. So okay. So a remark on this actually is that a lot of what I'm going to talk about today is how to do exact versions of multicore. And of course, if you don't allow communication, you introduce additional problems. But what the exact versions of this, what I'm going to call talking multicore, allow you to do is get some insight in how you can make good approximations for the case where you can't communicate. Okay, so that's the talk actually, or the very last part of the talk. There's another element to this which I'm not going to explore at all, which is these are sort of warehoused in two areas. You've got this idea of a single core approach, a multi-core approach. But actually, what you'll see later in the talk is if you employ just solely a single core approach, you have degradation, and it doesn't scale well in the number of cores you've got in addition, right? So you've got problems in the single core land, which is, you've run out of memory on your computer, all of that sort of stuff. But in multi-cores, the solution to your problem isn't just to split it into an infinite number of cores. That's not the solution either. And it's not necessarily the only architecture that you could explore. In fact, there was a talk very on in the week where there were sketching methods, and that's an entirely different approach to this issue. Okay, so the outline of my talk, essentially this talk's based on two papers. One appeared in Archive in September last year after a gestation period of several years and a lot of pain. That appears there. There's some extensions I've done to the first one, which I'll talk about. The second one, we have written a paper, which is unreadable, for this multi-core approach. Unreadable in the sense that it'd be difficult to read between the lines of equations. So hopefully during the month that I'm around here, it'll be something I can talk about with people that are interested. So today's only really giving you the gist of these two things. It's not something I could cover in the remaining 30 minutes. Okay. So the single core part, which is the first part of my talk, I'm going to introduce very briefly something called quasi-stationary Monte Carlo, which appears in Andy's poster outside. I'm going to talk very briefly about subsampling and then putting it all together, and it's everything put together which we call scale, which is this scalable method on a single core. The second part of this, I'm going to very briefly say, well, actually there's lots of different ways you can implement this, and here's an alternative way which might be more practical than the way we've got in the paper. Okay. The second part of the talk, what we're calling Bayesian fusion, this idea of recombining everything, unifying lots of separate analyses. I'm going to introduce something called fusion measure, and hopefully people haven't seen this before. And then I'm going to talk about how this actually admits consensus Monte Carlo as a special case, okay? Without all of the maths. There has to be some maths in there. Okay, so I found this cartoon online, and I thought this is a great way to alienate a lot of my audience. But I think the cartoon's actually relevant for this talk, in that we've put out there these papers which are admittedly far too long, and the idea of this talk is actually to condense it into what are the key ideas, the key novel parts of a research that we're saying perhaps it can be used by computer scientists who know how to use properly a computer for real algorithms for real problems. So if anybody's got any suggestions or are saying to us we're doing it entirely the wrong way, or have you thought about this, during this month please come and speak to me or any of my other co-authors. Okay, this next section I'm going to call retrospective trust. Retrospective because I'm going to give you some methods which exist in the literature, but very few people are aware of them because they may or may not be interesting. And trust because I'm not going to explain them. You just need to take it on trust that they're right, okay? So this section is called retrospective trust. Okay, so a lot of what I've done previously is on simulating diffusions. And this is a path of a diffusion, okay? Actually, this is just a path of Brownian motion. A single realization initialized from a single point. Now, a lot of times when people look at these continuous time processes, their instincts to immediately discretize them. And discretizing things introduces error. And what I'm going to tell you, and you have to take in trust, is that's not always the case. You don't always have to introduce error for simulating these objects. So, suppose I want to simulate from a particular type of diffusion, X, and I'm going to call the measure induced by this diffusion Q. Well, it turns out you can do two things. One is, if it's unconditioned on its endpoint, you can break it into lots of little chunks and simulate it iteratively. And the second thing is you can do an entirely discretization-free approach. And actually, it looks very clever, but all it is a rejection sampler, a very simple rejection sampler. You propose the endpoint from some density h. You propose parts of the path you're interested in from something with nice properties. So it might be Brownian motion, which I'm calling W, or say a Nornstein-Uhlenbeck process, which I'm calling O, and then you accept or reject it, or you assign it a weight, or you do something. And you return all of this, and it has no discretization error associated with it at all. Okay? Now, I've put various asterisks in places because the details are complicated, especially part number 3. The way you do this accept reject is you have an exogenous Poisson process, okay? But essentially it's a very simple rejection sampler, and it's possible to do it for a certain class of diffusions, like the one up the top. And actually, Jose, if he's somewhere here, maybe he's missing my talk. On Friday, he's going to give a fantastic talk where he generalizes all of this. Okay. Conditioned diffusions are even simpler to simulate from. You just miss out step one. Okay? And what you get out is something like this. So these squiggles are the underlying paths, which I can't look at because they're infinite dimensional, but you can get a finite dimensional characterization of them without any error. So that's trust part one. Trust part two is there's lots of nice properties of the Langevin diffusion which you can exploit in a statistical setting. So, what is the Langevin diffusion? In that diffusion I gave you previously, if you set alpha to be this quantity here, then that's what's called the Langevin diffusion. And it has a nice interpretation, or a nice property, which is it has invariant distribution nu. So it's nu here because I've got nu in the alpha setting. Okay? And actually you can use this in a statistical setting to explore some target distribution of interest. If I just set nu to be pi, and I'll call this Langevin measure, that's what the L is. If I set nu to be pi, it gives me a way of exploring a target density. What's that way of exploring a target density? Well, I just simulate the diffusion. And if t is very large, then x is going to be a draw from pi. Okay? And indeed, that's precisely how people come up with Mala. Mala is essentially taking this notion that you can set nu to be pi in this Langevin setting, discretizing it, discretizing introduces error, and then correcting for it. And then what you end up with is Mala, with all of the associated problems of embedding something in a metropolis type framework. It turns out that this rejection sampler I showed you in the previous slide is part, or the Langevin diffusion is part of the class of things you can simulate in that previous slide. You can do it. But it has a fundamental problem, which is step one in that rejection sampler. You need to be able to simulate it from something which is just as difficult as being able to simulate from nu to the power of half, or in the case of the direct statistical exploitation, pi to the half. So it's a problem which is just as hard as the problem you want to solve, right? And indeed, what you can do is you can write down what the transition density is for that diffusion, and what you see is you can decompose it into two parts. One part corresponds, the red corresponds to step one of that algorithm, which looks like simulating from nu. The second part's flipping a coin, and it has invariant distribution nu. So the pedagogy of this work is we said, well, perhaps we just miss out step one. Rather than simulating from w nu to the half, we just simulate from w. And rather than setting nu to be pi, we set nu to be pi squared, the so-called double Langevin measure. Do we end up with pi? That's where the pedagogy is. The next property, which will come in really important for the fusion stuff we'll talk about later, is this rather trivial fact, which is rather than starting my diffusion at a point, if I simulated the initial point of my diffusion from nu, or pi squared, and I evolved it according to the dynamics that I'm giving you, then for all t, xt is also a draw from nu. It's measure preserving. Okay, one slide on quasi-stationary Monte Carlo. So, this result here, this notion that I had nu being set to pi squared, how can we exploit this? So in the paper, in the scale paper, we've got a result which we call a quasi-stationary limiting distribution, which we exploit to reach quasi-stationary Monte Carlo. And essentially what we're doing is saying, consider Brownian motion, and we're going to kill it at some stopping time tau with intensity kappa. And kappa has this form. Then we're going to consider the quasi-limiting distribution. So we're going to look at t tending to infinity, and it's not yet died, right? So we're looking at this process conditional at not dying. Then under weak regularity conditions, this has quasi-stationary distribution pi. So this gives us another approach for trying to simulate from pi. The idea is we could simulate Brownian motion, kill it with intensity kappa, and conditional or not dying yet, we get a draw from pi. It's a really odd thing. and that's the statistical interpretation. The question is, why does this help you for big data? I'll come on to that. And how do you actually implement this? How do you actually implement it in the sense that I'm conditioning on an event which will happen with probability 1 some very far time in the future? How do you simulate something which is going to occur right in the tails of t? So, why does this help you for big data? So, it turns out this approach for simulating from pi, we're calling quasi-stationary Monte Carlo, is essentially equivalent to simulating Brownian motion and an inhomogeneous Poisson process with intensity kappa. That's what we're doing. That's what the algorithm is. The problem is, and the reason it's not directly applicable to big data, is each evaluation of kappa looks at pi, is an order n calculation. But let's run with it. If we were to implement this algorithm, how would we implement it? Well, you can't simulate directly an inhomogeneous Poisson process. So what do? We do Poisson thinning. We find some bound for kappa, which we'll call k. And to simulate a Poisson process of kappa, it's equivalent essentially to simulating a Poisson process of rate capital K and accepting or rejecting each point with probability kappa over k. Right? Where does subsampling come in? Well, here's the construction I'm going to give you. Suppose I can find some auxiliary random variable and some kappa tilde, which is bounded by k tilde, such that the expectation of kappa tilde is kappa, right? So this seems a bit odd. Then an alternative way of simulating a Poisson process of intensity kappa is to simulate a Poisson process of intensity k tilde and accept or reject each point with probability kappa tilde over k tilde. It's entirely equivalent in the sense that if you look at the randomness from the first scheme and the randomness from the second scheme, you wouldn't be able to tell them apart, right? So why might this be useful? It just looks more complicated. Well, if I can find some auxiliary random variable in kappa tilde which are easy to evaluate, cheap to evaluate, order 1, such that kappa tilde, k tilde over k scales well, then I'm going to have scalability in this quasi-stationary scheme. That's the full idea. That's all of it. And how might you do this? Well, remember, this kappa actually looks a bit like it's a simplified version of kappa, but kappa essentially looks like this. It's a big sum, right? So a very simple subsampler I could construct here would be I uniformly at random choose one of the data points, that's A, and kappa tilde would just be that evaluation of that single point multiplied by n. That would be an unbiased estimator. Directly, however, k tilde over k is not going to scale well. And so how do we get around that? We use a control variate. So that's quasi-stationary Monte Carlo plus subsampling plus a control variate gives you the methodology for what we're calling single core scalability. The next question arises in how do you implement this precisely? And this is a minefield. It turns out that I'm not very good at computers. I've broken this computer in every way you can possibly imagine. So in the paper, originally, we've employed what we call scale, and really a better name for it might be SMC scale, right? So the problem we're trying to address is that I'm going to simulate Brownian motion until such point that I kill it, but actually I'm interested in t tending to infinity, and I'm going to die before that, right? So what does SMC scale essentially to do? It solves this problem of trajectory death by either, depending how you interpret it, doing continuous time multi-level splitting or importance sampling sequential Monte Carlo type approach. And that's essentially it, right? There's a myriad of possible ways you could implement this, but that's what we're trying to do. We're trying to avoid trajectory death, and to do that, we embed it within SMC. So what do you get out? You get out something that looks like a particle filter. So if you do the importance sampling version of it, you're going to be simulating it to some point, then you resample and you simulate to some point, and resample and so forth. And in the limit, as t tends to infinity, these trajectories are going to look like draws from pi. And just like you would do with MCMC, where you take your ergodic average, you just collapse time and look at your occupation measure. Here you do exactly the same thing. You collapse all of the trajectories, you look at your occupation measure, and it will look like pi. Right? So that's SMC scale. The other approach which Divakar and Andy are working on is something we're calling regenerative scale, and it's based on a paper that Jose had with Peter Glynn. And here it's a lot simpler to imagine. You just have a single trajectory starting at 0, and you evolve it until such point that you die. So that's that first red vertical line. And when you die, you sample from your current occupation measure. Very trivial to do. You just sample uniformly between 0 and 2, and you regenerate. You just choose that point and you start again. And you do this iteratively. And this also has, conditional on solving all of the proofs, this also has the correct quasi-stationary distribution pi. So this is an entirely different way you could implement this. So, in summary, QSMC is exact Bayesian inference, exact in exactly the same way as Monte Carlo's exact, MCMC is exact. There's no intrinsic cost for exactness, and it scales well. The drawback is it's complicated and non-standard, and I'm putting lots of details under the rug. There exists no standard R packages, all of that stuff. But a lot of the ideas in here, I think, can motivate good other methods. Okay. That's essentially what I'm saying here. What am I missing out? Well, finding the bounds for this Poisson process is tricky. It requires lots of localization type arguments for Brownian motion. I've missed out all of the details in the theory for both QSMC and the different versions of scale that I've illustrated. We've not talked about scaling in terms of dimensionality, how you find the control variate, all of that sort of stuff. I've put under the lugs all the implementational details, and I'm not going to give you an example. I'm going to skip over it. Okay, the second part of my paper, we're calling multi-core or Bayesian fusion. What is it? Well, back to our original problem. We've got some target density which looks like this. This time, f isn't going to be a likelihood of an individual data point. F is going to be a sub-posterior or a shard, or I'm not quite sure what to call it. Capital C is going to be the number of cores I have available to me. There's other settings where this is interesting, not just for big data. Suppose, for instance, I wanted to pool expert opinions. One way of pooling expert opinions is to use something called the product pool. Or perhaps I've got information on some parameters of interest coming from lots of different sources. Chris Holmes talks about multi-view learning a lot. Perhaps this is a paradigm where you would have this type of structure. Or perhaps you could induce it. Perhaps you've got a graphical model and you can find some structure in your graphical model, and it turns out you can put it in this form. So this arises in lots of different ways, but I'm going to call F my sub-posterior. Now, here's a very simple approach for simulating from pi, and this is meant to be illustrative. And when I show you this, you're promised not to laugh and think about ABC, or actually ABC without the approximation. Here's my algorithm for simulating from pi. What I'm going to do is I'm going to simulate x1 from f1 all the way up to xc from fc, right? And I'm going to keep on doing that until they're all equal to one another. Okay? Not the most practical algorithm. Otherwise, I'll go back to 1. And if they're all equal, I'll return x. And it turns out x is going to be a draw from the product of these densities, which is proportional to pi. So this is a very simple algorithm for simulating from pi, completely impractical in real life, but you could certainly do this. I gave you my toolbox of tricks, retrospective trust at the beginning. The extension to this algorithm I'm going to have is, I'm going to say, recall at the beginning this property of the Langevin diffusion we had. which was if I could draw x from nu, then for all t, xt's from nu. Right? This trivial property. And then I'm going to introduce tons of notation. I'm going to say let L1 be the Langevin diffusion associated with sub-posterior 1, let L2, blah, blah, blah. DL is going to be the double Langevin associated with the first posterior, so on and so on. Right? So I'm going to introduce all of this notation. And what I'm going to tell you is, now I'm going to draw x1 from f1 and x2 from f2, but rather than doing this accept reject procedure, I'm going to propagate them in continuous time using the associated dynamics given by the Langevin equation. Right? So I might get something like this. So why is this interesting? So I've got, say, f1 is the black path, f2 is the red path. Well, it's not that interesting, but what might be interesting is if you think about all of the times these paths cross one another. Now remember back here we have that for all t bigger than 0, xt is a draw from nu. Well, it's not a huge leap of faith to see that actually the points where these paths cross is a draw from the product. So if I was able to simulate, in this case, two paths, and look at only the times where they cross, and use those as my draws, those would be draws from the product of f1, f2, which would be pi. So this gives me another completely impractical scheme for simulating this. So why is it impractical? Well, it's impractical because this is tricky enough in one dimension. In more than one dimension, the chances of two paths hitting one another becomes more and more difficult. And in higher than 2 dimension, it's not even going to happen. The other problem is that this is difficult enough for 2 paths, never mind 3 paths or 4 paths, and we want C paths. I want 10,000 paths. So how do I shoehorn all of this methodology? How do I find some framework for exploiting these ideas that I can use in this truly multi-core setting? And the graph I'm going to show you, which might make you feel slightly seasick, is this one, right? So what I'm showing you here is a whole collection of paths. I'm not telling you how I simulate them, but what I'm doing is I'm fusing them together at the end point, right? I'm going to make them all hit the same endpoint at time t, okay? And I'm going to construct this in such a way, this huge object, such that if I only look at the time marginal t, then this is going to be a draw from pi, right? And the idea goes directly back to multi-core. I would do each one of these paths in isolation using a subset of the data on itself, and then I would try and fuse them together. That's what I'm going to try and do. So, some details, and I've taken out as much maths that I could get away with without it being completely incomprehensible what's going on. What's happening here? How might you do this? Well, I'm going to redefine these paths slightly. So suppose I was simulating all of the paths but without any constraints. I'm just simulating from lots of Langevin diffusions. I'm going to reformulate it, and I'm going to call xt1 yt, and all of the other paths I'm going to look at the relation with that endpoint, right? So I just define xtc to be yt plus some delta c, right? And I'm going to think about the space of all paths where this distance goes to 0. So all of these paths are fusing together. And I'm going to introduce something called fusion measure. Okay? This is fusion measure, and it looks horrendously complicated. And it is horrendously complicated. What I'm doing here, and the way to interpret this, is I am taking... Yeah, it doesn't have a good interpretation. We came up with this retrospectively, so we came up with this in order to get the result we want, but the way you can think about this is a bit like this graph. This might be a realization of fusion measure. And essentially what it is lots of paths connected to a biased endpoint. The biasing of the endpoint looks like 1 over pi. The initial points look like f squared, and all of the paths are joined together using a double Langevin diffusion. So it's a horrendous object. But it will come clear why we're using this object, hopefully. So I'm calling this fusion measure. Okay. So now that I've came up with this ridiculous piece of notation, the key idea here is that if I was able to draw a collection of paths from fusion measure, and look at xt, then it's a draw from pi. And the way you can see this is if you take fusion measure and integrate everything out apart from the end point, you get lots of cancellations and you get pi. So the statistical algorithm that comes off the back of this is if I can find some way of simulating this collection of paths from fusion measure with lots of practical constraints, like I don't want lots of communication, then this would be an approach to solve this standard multi-core problem. Okay? So somehow these problems are equivalent in some inverted comma sense. Right? So how might I get a draw from fusion measure? Well, I'm going to use rejection sampling with proposals from some measure that I can interpret and I know how to simulate and has all of the technical details like equivalence diffusion measure. Okay? And I'm going to call this measure P, or proposal measure. So what would you do is you would, rather than simulating curly x from f, what you would do is you would simulate curly x from P and you would accept reject with some probability, just a rejection sampler. And what are the things I can choose? Well, there's essentially two things I can choose. One is Brownian proposal measure and one's Ornstein-Uhlenbeck proposal measure. And what are these? Well, these are essentially, if you look at this H, all it's saying is choose the endpoints in some way using density H, and then connect everything together using either Brownian motion sample paths or Ornstein-Uhlenbeck sample paths. And this is what this is doing. So in the simple Brownian motion case, what is this precisely? Well, the rejection sampler looks a bit like this. If you choose the optimal way of, if you choose H, this first part, H in Brownian, if you choose H in the optimal way, then you can interpret H. H is draw one point from each one of the cores and draw the end point from this endpoint draw density, which looks a bit like a perturbed Gaussian. Right? That's how you do it. You would draw one point from each one of your cores and a perturbed Gaussian, and then you connect everything together using Brownian motion sample paths. Now, of course, you can't simulate directly from H, and so you would have another rejection sampler. You need a rejection sampler to do this endpoint draw. And once you've done this, you connect everything together using Brownian motion sample paths, and you accept or reject with this probability. Right? Now, by some quirk of fate, this kappa, which I've put in red, is exactly the same kappa as you get in scale. So there's some deep connection here. Okay, so, yeah, I'll be almost done. So, this is essentially the multi-core approach. It's a rejection sampler. You construct this extended space which admits as one marginal pi as the marginal. And then you construct a way of simulating from this very complicated measure, and it's essentially just a two-stage rejection sampler. You simulate from the starting point, you simulate from the ending point, you connect everything together, and you accept, and you can do this exactly with this probability P of x, curly x, right? And to do this, you would end up with an exact fusion, right? However, I'm calling that talking fusion. To do the exact fusion, accept or reject with probability P of x, you would need to let all of your cores talk to one another, or at least the individual cores talk to the mother core. So an approximate version of this would be to approximate P of x such that this doesn't happen. Now, you can do this with the Ornstein-Uhlenbeck process as well, and as a special case, H is precisely consensus Monte Carlo. And P of x tells you in what way you have to do your correction to your draw in order to get an exact draw from what would be consensus Monte Carlo. But it tells you some interesting things, right? It has exactly the same form. So what happens to this acceptance probability is it degrades as you increase the number of cores. As you increase t, as you try and force together points which are actually very far apart, it degrades. It looks less and less the thing you're trying to simulate from. However, P of x is precisely 1 in the case where you have an Ornstein-Uhlenbeck process and your target and your individual sub-posteriors are actually Gaussian. So it recovers consensus Monte Carlo as a special case entirely. And to illustrate a very, very simple non-big example of this, this is trying to use this to simulate from a beta 5 density. And I've split it into 5 cores, or Hongsheng split it into 5 cores. He did the simulation. So what is the beta 5 density? It is the black line. It's the one sort of in the middle. And superimposed upon the black line is a blue line, which is what you get if you use exact Bayesian fusion, the fully talking version. If you use the approximate version of the algorithm, where you don't bother doing the correction, with a Brownian motion proposal, you get the blue dotted line, the blue dashed and dotted line. The red dotted line is what you get from consensus Monte Carlo. And if you to use the same idea inspired by consensus Monte Carlo, which is to use an Ornstein-Uhlenbeck process and try and approximate properly this acceptance probability, is you get the dotted blue line. So what you see here is for this very simple density, there's no big data in it whatsoever, is something like consensus Monte Carlo or typical big data multi-core approaches. They don't work even for some specific small examples. However, you can understand how to recover the truth, and you can understand how you get from an approximate version to a more exact version. And that's what we're calling Bayesian Inference. And that's me finished.
What happens if you don't have them exactly meeting? Can you have a region?
You could, I guess.
What happens?
It's not something I've really explored, but I mean, some of the sketch I did right at the beginning of this really naive algorithm is a bit like exact Bayesian computation, and essentially your question goes down those lines. I mean, you'd be introducing an error in some form. You need to understand how this error moves forward. But these sort of ideas, you could in principle do something like that. Okay.
I have one question. What if the posterior distribution from each machine is a discrete one that is obtained by some approximation, some Monte Carlo approximation?
Well, then in the exact setting, you're not getting a draw from the product of S. You're getting a draw from the product of F tildes. So it's exact again in the same sense that MC is exact as, you know, assuming that.
More questions?
What in terms of the dimension of x, your examples obviously, you know, for a talk they're all one-dimensional, so we can see what's happening. But have you tried this and
we've tried it in various forms of logistic regression. I mean, what you see actually is this P of x is an explicit representation essentially of the error you've got in your model if you don't do a correction. So if you were just to work with a vanilla multi-core method and not do the correction, this P of x lets you understand where you're going to go wrong. Now, essentially where you're going to go wrong, and it comes back to this kappa, in higher dimensions or over longer periods of time, there's a bigger mismatch between what you're actually trying to simulate and what you've actually simulated. And this is exacerbated in dimension, it's exacerbated in time, it's exacerbated in the number of cores you get. So as you move into bigger and bigger dimensions, this P of x is going to become increasingly small, and this sort of illustrates actually precisely why you need to be reasonable with the number of cores you choose. You need to be reasonable with all sorts of things that you're attempting to work with.
if you had to guess the bounds of practicality, what are your thoughts?
Oh, I don't know. This is an expert in computer science ought to be the one that does that. What I can do in my computer and what people can do in practice are different things.
That's just to relate to that. I mean, I think one of the things about this method being a continuous time method is that you know, you can always do things in smaller chunks. And so just in the same way that kind of continuous time SMC algorithms scale much better because you've got that flexibility. You've got this for all these exact algorithms and therefore these things. So the hope would be that you can get something that's polynomial in dimension, which is what you get for the exact algorithms. But we don't have any formal results on that.
Speaker?